My name is Đức Kham, representing for Group 12, here to present to you our presentation on embedded systems, addressing the need for efficient, intelligent control. Onto the first part of our presentation is problems introduced before the existence of embedded systems. Before the emergence of embedded systems, digital control and automation relied largely on general-purpose computers or discrete electronic circuits. Early control mechanisms in industrial automation, communication, transportation, and consumer electronics were cumbersome, expensive, and lacked flexibility. Systems were built using large, specialized hardware units such as relays or analog controllers, which offer limited functionality and poor adaptability. These systems could not easily accommodate complex real-time control or multitasking, and they required significant manual calibration and maintenance. Moreover, general-purpose computers, though capable of handling more sophisticated tasks, were unsuitable for integration into compact or portable devices due to their size, cost, and high energy demands. In the 1960s and 70s, digital computers used for automation consumed large amounts of power and occupied entire rooms, which made them impractical for embedded control applications such as automotive systems or consumer appliances. The lack of miniaturized task-specific computing created barriers for integrating intelligence into everyday devices. Another major problem was the absence of real-time responsiveness. Traditional computing infrastructure operated on multitasking operating systems optimized for throughput, not deterministic timing. As a result, they could not guarantee immediate responses to sensor data or control inputs. This posed serious limitations in environments that require critical safety measures, such as aerospace, healthcare, automotive control, where even millisecond delays could cause failures and, in worst-case scenarios, possible casualties. Furthermore, early systems suffered from low reliability and poor tolerance on environmental stress, making them unsuitable for continuous operation in harsh industrial or outdoor conditions. Onto the second part, are why the problems need to be solved. Why are these essential? The growing complexity of mechanical and electrical systems during the late 20th century created an urgent need for efficient and intelligent control. Industries demanded faster, smaller, and more reliable control solutions to enhance productivity while safety while reducing costs. As devices became more sophisticated, ranging from cars and aircraft to household and electronics, the requirement for precise autonomous control systems grew exponentially. One major driver was miniaturization. Advances in semiconductor technology enabled the production of microprocessors and microcontrollers, making it feasible to integrate computing capabilities directly into small devices. This shift was critical for developing compact products such as mobile phones, washing machines, and medical instruments, where external computers were impractical. Cost reduction followed naturally from this miniaturization. Smaller task-specific chips could replace complex hardware assemblies, lowering both manufacturing and maintenance expenses. Power efficiency also became a central need. As battery-powered and portable devices gained prominence, systems required low-energy operation without compromising performance. General-purpose computers were highly inefficient in such scenarios, as their architectures were not optimized for limited resource environments. In contrast, specialized embedded architectures promise significant power savings by executing only the operations necessary for their assigned functions. Furthermore, real-time responsiveness and reliability were not negotiable for many emerging applications. Automotive braking systems, robotic manipulators, and medical monitoring equipment all demanded instantaneous and predictable control. Non-deterministic delays from general-purpose operating systems were unacceptable in such contexts. The need for deterministic timing behavior directly motivated the design of real-time embedded systems that could respond to environmental inputs within fixed deadlines. Finally, the integration of intelligence across all levels of modern infrastructure necessitated localized computing power. The proliferation of sensors, actuators, and network devices made centralized computing impractical. Instead, distributed embedded systems became essential to process data and make autonomous decisions at the device level. This architectural evolution laid the groundwork for the Internet of Things and smart systems, both of which depend fundamentally on embedded computing. Therefore, the convergence of these technological and functional demands, the drive for miniaturization, efficiency, real-time capability, and distributed intelligence, created a clear need for the embedded systems paradigm to emerge and flourish. And third, the core purpose of embedded systems. Embedded systems exist to meet the critical need for efficient, dedicated computing within physical devices. Their primary purpose is to provide a compact, reliable, and optimized platform for executing specific control or monitoring functions. Unlike general-purpose computers, embedded systems are designed with a single or limited set of objectives, allowing engineers to tailor both hardware and software for maximum performance under given constraints. In essence, an embedded system integrates computation into the fabric of a device. It connects sensors and actuators to a central processing unit, enabling the device to sense its environment, process information, and act autonomously. By embedding computation locally, systems gain the ability to operate in real time, even under strict resource and energy constraints. This integration allows embedded systems to achieve deterministic performance, which is essential for precision and time-sensitive applications such as industrial automation, automotive control, telecommunications, and aerospace systems. Embedded systems also serve to enhance reliability and resilience. Their hardware and firmware are designed for continuous operation, even in demanding environments where failure is not acceptable. Because they are built for specific functions, unnecessary complexity is eliminated, reducing potential points of failure. Moreover, by incorporating fault-tolerant design and low-level control over timing and memory, embedded systems can maintain stability and predictability, qualities indispensable to medical devices, flight control systems, and industrial robots. Another key purpose is energy and cost optimization. Through the use of microcontrollers and system-on-chip architectures, or SoCs, embedded systems deliver high functionality with minimal power consumption and manufacturing cost. This makes them suitable for mass production in consumer and industrial markets alike. The ability to design application-specific integrated circuits, or ASICs, and optimize firmware ensures that every computation cycle and memory access serves a precise functional purpose, improving both performance and efficiency. In summary, the purpose of embedded systems is multifold: to integrate efficient computation into physical systems, to ensure reliable real-time performance, to minimize power and cost, and to enable intelligent, autonomous behavior across diverse domains. They represent the convergence of hardware and software design principles, optimized for dedicated functionality, fulfilling needs that traditional computing architectures could not address. And as technology continues to advance, embedded systems will remain central to innovation, powering the next generation of smart, adaptive, and interconnected devices. Thank you for listening.